This is a 36th lecture, and today I'll discuss the built-in potential, or it is also called the barrier potential or contact potential when it is the same thing. I have already discussed this point with you in the previous lectures where I started the PN junction with you. And see, this is a PN junction, for example. Let's take this as a PN junction diode. And when I said that there's an open circuited one, for example, if there's a open circuit, there's a PN junction here. This is P layer on this side and this is N layer on this side. This P layer is formed by adding acceptor impurities, and every acceptor impurity, it accepts an electron and becomes a negative acceptor ion. Negative acceptor ion. Acceptor impurity becomes a negative acceptor ion with the release of a positive hole. And it releases a positive hole. So on P side you have majority of holes, and on N side it is formed by doping it with a donor impurity. Every donor impurity releases its fifth electron and it becomes a positive donor ion. A positive donor ion, and every donor impurity, it releases an electron. So on N side you have majority of electrons. I'm repeating this. At the junctions, near the junction, due to the diffusion of charges because of non-uniform charge density, the charges diffuse from higher concentration to lower concentration. Suppose this charge, it moves towards this side, or this charge moves to this side. So leaving behind only on this side, you will have only the immobile charges here. You will have immobile charges here, negative, and here also you will have positive immobile charges here, which are nothing but simply the donor and acceptor ions. And because of this, I told you that a potential is developed here, and this potential is called the barrier potential VB, or the contact potential, built-in potential, barrier potential, or contact potential, which is represented by this VB or VT. And remember that this is the condition in open circuit case. We generally consider this as in the open circuit case. When it is closed circuit, when you close this circuit either by forward bias or by reverse bias, accordingly this VT, this barrier width, or I can say this depletion layer width, will increase or decrease depending upon the type of biasing it is. But here we are interested that under this unbiased condition, what is the value of this built-in potential VB or VT. And this VT, I'll just derive it. It is given by KT upon Q log to the base E, which is also represented as Ln, NAND upon Ni square, and my target is to derive this only for today. I'll derive this. Now let's see how we go for the mathematical expression for this. Suppose I say that this is the PN junction here. Say this is your PN junction. This is P side. Let's take this is a PN junction. This is a junction, and this is your P side, and suppose I say that this is the N side, and this is your depletion layer where the built-in potential is developed. Of course, on P side you have negative charge carriers. Of course, you have these negative acceptor ions, and here you have the positive acceptor ions. And I am interested in this voltage, this built-in potential here, or this contact potential, or this barrier potential here. Now of course I'll consider that the PN junction is unbiased. Now when this PN junction is unbiased, it is unbiased means if this is a PN junction, this is P and this is N, and this is unbiased. Unbiased means this is open here. It is not connected to any battery. So it means that the current flowing in the external circuit is zero. That is the current density. which is equal to 0. So I can say that under this condition, for unbiased condition, the current density J will be equal to 0. Now, in any semiconductor, I told you that the current density or the current is mainly due to two factors. Of course, it is the sum of two currents, I can say, that is the current due to electrons and the electron current and the hole current, and say it is because of this, I say electron current by Jn, and this hole current I am representing this by Jp. So I'll consider any one, either electron current or hole current. So let's consider for holes. Suppose I consider for holes. Of course, Jn plus Jp is equal to 0. I assume that this, of course, for holes, I assume that this Jp is equal to 0. Under unbiased condition, of course, this current is 0. It means the electron current is also 0 as well as the hole current is 0. I am considering holes. It can be done with electrons also. So I consider that this is equal to 0. Now, this current density, as I told you, in case of semiconductor, there are two types of current. One is called the diffusion current and the other is called the drift current. So I can say this implies that the hole current, the drift hole current, I am writing this as Jp drift plus I write this Jp diffusion. That is the sum of drift current as well as the diffusion current. The sum of these is equal to 0. Now, if you remember, I told you that the drift current, this drift current, J drift, if you remember, this J drift is equal to sigma E, and the diffusion current for electrons and holes, let's talk about the drift current, then the sigma is equal to mu into n into E, and this factor into E. This is for in general for a conductor. If I take for a electron, it is n mu n into E, and for hole it will be, in spite of n, this is p, this is mu p, electronic charge is E, and this factor is equal to E. I hope that I have already discussed this with you, where p is the hole concentration, number of holes per unit volume. So I am writing this drift current as, so I can say that this drift current, I can say that this is equal to p mu p, where p is the hole density. I am not writing it, I have discussed many times. P mu p into electronic charge, which is E, and electric field is E. Sigma E, this drift current is equal to sigma E, and value of sigma is equal to mu n E. In place of mu, this is mu, it is mu p. In place of charge density is P, and electronic charge is E, it is equal to this much. And plus, this is equal to, if you remember, this diffusion current is equal to, for holes, it was minus of dp, of course electronic charge or the hole charge, electron charge same, into the diffusion constant dp and dp upon dx. This is equal to this much. Or from here I can say that, of course, this E will cancel, is equal to 0, is equal to 0. Then until this will cancel, I bring it on the right hand side, this cancels. So you'll have P mu P into E. This implies that, alright, this implies that P into mu P into E is equal to dP into dP of dx. Now just see that what is this, these holes are moving from, if I say that this is the positive x direction, displacement is in this direction. If you see these are holes, they diffuse from P region to N region, they are moving in this directions, means this P is a function of x. I can say this P is nothing, it is a function of x only. And of course E already we know, E is V by L or V by X. It is already a function of, it is the potential gradient, potential per unit length. So I can say that this is V by L. This is equal to this much. This E is equal to V by L from here, I can say it is simply this much. So from here I can say that this, I write this as a function of S. So I can say that this is equal to, I'm writing this E on this side. This E is equal to, I'm writing this as dp upon mu p, dp upon mu p, 1 upon this p. This p I'm bring on this side. Of course it is a function of x, and d upon dx, and this charge concentration is a function of S, as it is diffusing from p region to n region, or from n to p, from higher concentration to lower concentration. It is equal to this much. And of course if you see that this, I can say that this is d upon dx in a very small area. Suppose I say this is very small length dx. So this E, if you see, I can say, I can write this E is equal to minus, I can say that this E is equal to minus d upon dx of V, of course, which is a function of x. This L, I think small length is a very small length dx, very small distance dx, in spite of this long length L, I am taking this as dx. So d upon dx of Vx, of V. So I hope that this is clear to you. So I write this equal to this as, and this implies that, or I write it here, this implies that this is d upon dx of applied voltage of this V, whatever potential is developed here in this small region, this V x, is equal to, now dp upon mu p. If you remember, I told you the Einstein relation. One relation was Einstein relation, where we discussed that dp upon mu p is equal to dn upon mu n is equal to kt upon q. This is the Einstein relations which I discussed with you, and this is what I substitute here, that this dp upon mu p, I am writing this as kt upon q. This is kt upon q, 1 upon p, which is a function of x, d, which is a function, dp, which is a function of x. I hope this is clear to you. Now although we don't cancel it like this dx and dx, this cancels. So I can say this implies that this v, d of vx, d of vx is equal to kt upon q into 1 upon p, which is a function of x, d of px. Now I need this potential here. I am interested in this built-in potential Vx. How much is this between this point and this point? I am interested in this here. What is the built-in potential here? Now suppose I say that this is p side, it is Vp on here, voltage at this, and on n side this voltage is Vn. Now in order to find this, I integrate this. This is constant, so I integrate this here. Now look at this. The initial value of this is Vp, so I can say the limits are Vp to Vn. Of course, one minus sign I missed here. Minus of this much. Minus of this much. This is equal to minus of this much. So my Vp upon Vn. And of course, if I find from here Vn minus Vp, I can say that this Vt which I am interested in, this Vt is Vn minus Vp. This is what I am interested in. This Vt, I say this as Vt or Vb, is this potential minus this potential. It is equal to this much. And look at this. Suppose I say in P region, suppose I say that I am talking about holes. So I say, suppose the holes in P region, I represent this by P of P, means holes in P region, and these are the holes in N region. P represents holes, and this suffix P or N represents what type of semiconductor is this. So I am representing the holes here as P of P, and here P in suffix, this is N. So since there is a transition, there is a diffusion of holes from this region to this region, so I can say that the initial condition of this is holes in P region and the holes in N region, P of N. This implies that if I solve this, I am solving it here. this will be V of x. So minus V of x, and the limit is Vn Vp lower limit and Vn is the higher limit, is equal to kt upon q. dp of dx 1 upon px dpx will be log of this much. So I can say that this is equal to log to the base e, because this growth is exponential in this thing, log to the base e, and it will be p of x. If you see, it is simply log to the base e of this function, and will have, of course, limits. This limits is pp to pn, pp to pn. I am rewriting this, or okay, let's continue here only. Or from here I can say this will be Vn minus Vp minus of Vn minus Vp, which is equal to this Vn minus Vp is nothing, it is equal to the built-in potential. I have found it from here. It is equal to kt upon q log of this minus this, or I can say log of Pn upon Pp. Now in order to remove this sign from this, I have to make it positive, so I can write this as Pp upon Pn. This implies that this is Vt. I'm writing this as, this factor is nothing, it is your built-in potential Vt or Vb. So I can say that this Vt is equal to kt upon q, kt upon q. This is equal to kt upon q. I can say I have removed this minus sign from here because this is log pn minus log pp. I am writing this log pp minus log pn, and I remove this sign from here. I am skipping few steps, so it will be l log to the base e, of course, and I am writing this log to the base e as ln. That is the natural log, is written as ln pp upon pn. Where pp is the number of holes in p region and pn is the number of holes in n region. So I can say that this is the barrier potential I obtained from here. Or one more thing, if you look at this, this implies that this Vt is equal to kt upon q. I am finishing in this page only. Kt upon q, pp, if you see, p is the number of holes. Now look at this, I'll show you in a different page. I am interested in pp and pn. Look at this, this pp is what? P of suffix p is the number of holes in p region, and this is nothing, it is the majority charge carriers, which is equal to Na. These holes in n region is equal to the, approximately equal to the acceptor concentration, and the holes in n region I have discussed with you, it is equal to Ni square. It is equal to Ni square upon Nd. Holes in n region is equal to Ni square upon Nd. So I substitute this here. I am substituting this here, kt upon q into ln. Ln means log base e. Pp is Nd. Pn is Ni square, sorry, Pp is Na, I'm not N. Pp is Na. Pp is the majority charge carriers in P region. It is of course formed by adding acceptor impurity, so the number of holes are approximately equal to the acceptor concentration, and this Pn is Ni square upon Nd, so it is equal to Ni square upon Nd. So this is equal to this much. I hope that this is clear to you. Now one last point I'm writing here only. This is the built-in potential. Now we have seen that the forward characteristics of a PN junction diode is like this. and we say that this is the knee voltage, and it is equal to 0.7 volt for 0.7 volt for silicon, and it is 0.3 volt for germanium. But this is under certain conditions. Actual value is this. Under certain conditions means if I take this T is equal to 300 Kelvin. First of all, in this equation, if I take this T is equal to 300 Kelvin, and if I take the value of for silicon, if I take this Na is equal to Nd, and if I say it is equal to 10 to the power 16 per centimeter cube, this is the impurity concentration, and Ni is equal to 1.5 into 10 to the power 10 per centimeter cube. This is standard value. If the intrinsic concentration for silicon is this much, and if I do the doping at this level at 300 Kelvin, then the value of this Vt for silicon is 0.7 volt, which we generally take. And of course for germanium, for germanium, if I take same value, Na is equal to Nd, that is equal to 10 to the power 16 per centimeter cube, first of all. And secondly, the value of Ni is equal to 2.5 or 2.4 into 10 to the power 13 per centimeter cube. Then under these conditions, if Ni is this much and doping is done at this level, then at room temperature, the built-in voltage, this knee voltage for this germanium, or this built-in voltage or barrier potential for this germanium is 0.3 volt. It is under certain conditions. Practically you'll never find it equal to exactly 0.3 or 0.7 volt, because there is some deviation in this doping level, as well as it is never always 27 degrees centigrade, that is room temperature. So you'll find some deviation from 0.7 or 0.3, but for numerical point of view, we take these values as the barrier potential for silicon is 0.7 volt and for germanium it is 0.3 volt. So with this, I have almost come to the end of this unit. I'll start with the next unit, or I'll start with the next topic in the next lecture. So thanks for the time being.